What's going on, everybody? This is Mr. Diamond, and I realized after doing the last video that I want to do an extra supplemental video to go with this, where I'm going to talk through all of these VSEPR geometries here. So again, valence shell electron pair repulsion theory is the idea that because bonds contain electrons, electrons are going to try to be as far away from each other as humanly possible. So I want to kind of walk through this whole chart here and look at an example of each one of these. So the first thing you'll notice is that anytime there's just two things, so let me take this and I'm going to take we'll call this our center atom, and then we'll call this a hydrogen here. Anytime it's attached to one atom, and that's it, it's made out of only two atoms, it's always going to be linear, because no matter how I flip this, turn this, rearrange it, move it around, it's still going to be a line. It's still one straight line connecting them. Even if I were to add electrons to it, which I've been using these longer, more flexible ones to represent them. Let me get that going here. So even if it's got these electrons here, because these electrons are not bonded to anything, we only care when we're describing our geometry, our molecular geometry. We only care about the actual molecule, the atoms. We don't care about the electrons in the shape. We care about them in how they make the shape, but when we are describing what we see, we don't describe the electrons because they're not another atom. So these two things here are just going to be a straight line. No matter how I flip this, turn this, rearrange it, it's always going to be these two pieces, these atoms, which are the only things we care about, are going to be a straight line. So it's going to be linear. Now looking here, the furthest apart it can possibly be, and I have to switch to this different center atom because it's got the holes in the correct spot for this, so to speak. The furthest away that two electrons can be is on opposite sides of the atom. So if there's only two bonds you're making room for, if there's only two things that you have to account for space-wise, they're going to be as far away from each other as humanly possible. There's no other things here in the middle that need to be accounted for. They are just as far away from each other as possible. So the angle between here is going to be 180 degrees. Now, I mentioned in my example video, technically linear, you're not really describing an angle because there's only two atoms and you need 3 points to make an angle, but we're going to still call it 180 because it's a straight line, just like this one. This linear is also 180 degrees from here to here. Now, if we have three things, your brain is going to tell you, well, we've got to get them as far away from each other as possible. The furthest away that I can get them is going to be if it's flat. So again, notice this is a steric number of 2. And I mentioned in the other video, well, there's no box here for one lone pair. Well, if there was a lone pair over here, if there was unbonded electrons, we're now down to two things. So it's got to be linear because it's only two things. Going to this next section right here, we've got trigonal planar. So what happens if we have three things with no dots? Well, I'm going to switch back to a different one. Now, I'm going to switch and I'm going to use this one. I'm using this specific, actually we'll use this one. Yeah, we'll use this one. Now, I have to use this one because, and I have to use the flexible bonds because I don't actually have a molecule in this kit that will make this shape. This shape is not super common among single bonds. So if I do this, I have to actually push it down. But what we can do to represent them is I can actually take and I can make one of these a double bond. Because again, steric number, as far as steric number is concerned, so when you're doing steric number, single, double, and triple bonds all only count as one thing, and a pair of dots also count as one thing. So while I don't have a shape that will let me do single bonds, I can still do a steric number of 3, but not include just single bonds. So I'm going to go ahead and add in and I've got this shape. Now this shape is a steric number of 3. This is a double bond because it's got two pieces attached to it, but it still counts as a steric number of 1 because it's only one atom that I've got to make space for. So I've got 3 total atoms. The optimal way to arrange 3 total atoms is going to be as far away from each other as possible, 120 degrees. It's going to be like a Y shape, or do it that way. It's a little more symmetrical. It's going to be this Y shape or this peace sign shape there. Now, if I take one of these off, so if I remove this and were to replace this piece with electrons, I mentioned on the other video, but to go into more detail about it, these electrons are going to fly around like crazy. So normally this would still be 120 degrees here, but because these electrons are so annoying and take up so much space, these atoms here are actually going to try to push a little bit further away. These electrons are nice, neat bonds. They're not actually in straight lines, but they're at least in bonds. These electrons are flying all over the space, all around, taking up a bunch of space. So it's actually going to force these things to push just slightly closer together, just a little bit closer together. So that's why we say it's a less than 120 degree angle between those two. Okay, going to the next one, we've got tetrahedral. So I'm going to go ahead and I'll just get the whole different molecule here for convenience sake. So if I have 4 pieces, I went into detail about this in the video, but your brain might tell you we could do a 90 degree angle, but that's not actually correct because we have to remember these are 3-dimensional. So because they're 3-dimensional, the shape that we're going to make is going to look like this. It's called tetrahedral. Tetra because it has 1, 2, 3, and then the bottom would be 4 sides if we were to make this a shape, which looks a lot like, because I'm at home, I can actually get this. Any of you who are D&D fans can get out a 4-sided dice. So this is a 4-sided dice that I've got, and it is a tetrahedron. It's got 1, 2, 3, 4. Tetra is a term that means 4. Hedron is shape, so it's a 4-sided shape. And if you notice, that's basically the same shape that this thing is make. It's got 3 things along the bottom and a point on top. So this is the optimal distance they can be. We can't actually just look and tell what it is, but this angle right here, although it looks like it's going to be about 120 degrees, it's actually going to be a little bit different. In this case, it's going to be 109 degrees, just a little bit smaller. Now, same thing's going to happen if I replace one of these with a pair of electrons. Those electrons are going to take up a whole bunch of space, and that whole bunch of space that it's taking up is going to push these things just slightly closer together, so it'll make this angle less than 103. And in this shape, and this up here was called trigonal planar, because it had trigonal, or trigonal meaning 3 things, and then planar meant it was flat. So this is completely... If I get back my other one, so it's just an actual molecule, this is flat. It's not because it's resting on, it's got the shapes here, but if I were to hold this up, this is a flat shape. And if I turn it sideways, you can see they're all on the same plane, more or less. But this one, if I hold it up and try to kind of straighten it out, you'll see they're not on the same plane. All 3 of these dots are slightly below this. So we don't actually call this a trigonal planar, we call this a trigonal pyramidal. And then again, these electrons are going to take up a whole bunch of space, push them together, so it's actually going to be less than 109 degrees for that one. And then finally, if I take off one other one of these and I replace it here, this is actually representing the structure that water will go form in. Water, if these were 2 hydrogens and if this was an oxygen, I'd have 2 lone pairs of electrons flying around up here that would push these things just very slightly closer together, a lot like what happened up here with this rare bent shape here. It's got a steric number of 1, 2, 3, 4, 2 lone pairs, 2 lines, 2 lone pairs, 4 total things, 2 lone pairs, 2 lines. We've got a bent or angular shape, and that's going to be a less than 109 degrees. It's going to be still below 109 degrees, but it's going to be even smaller than this shape was right here. So I hope this brief little video maybe helps clear up some of the stuff with it. I realized that I was going to do this in class, but then I wasn't going to be able to guarantee I was going to have time in class, and I wanted to make sure all the AMI kids were able to see this. So that's what I got for this video. If you have any questions, please send me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.